The logic gate in this lesson is the same as the previous one, but with the exception of the inclusion of a transistor. In the 1900s, these were large devices that used huge amounts of energy. This was followed by smaller devices using different materials with a much higher efficiency and speed. Nowadays, the sizes are so small, it's impossible to view them without some sort of magnifying equipment. Logic gates can be found in RAM, processors, and ICs or integrated circuits. They all work on a combination of transistors to produce logic gates. If we peer into an IC, we can see rows and rows of transistors. Each one normally has 3 wires, called a collector, base, and emitter. This is a schematic diagram symbol for the transistor, and we shall look in depth on some of its other properties later. But basically, current is unable to flow from the collector to the emitter, just like an open switch. However, when the signal is received at the base of the transistor, a path is created between the collector and emitter, just like closing the switch. This does oversimplify the principles of the device, as it also needs protection using a resistor, and it is polarity dependent. But for our purposes, it is adequate for now. Also, in practice, the transistor does not change its colour. We shall see how all this comes together in our practical arrangement. To return to our original logic buffer gate as shown here, and alter the circuit to accommodate the transistor. Also, we should include our truth table to display and explain our results. Once again, here is our direction of the electric route. We can see here through the simulation that the route ran through R1 and stopped at SW1, the switch, so that it was not able to complete the circuit to the base of TR1. But as there is still connectivity in the circuit, the electric route continued through R2 and LED1, but because TR1 is still off, the circuit cannot be completed and the LED fails to illuminate. Therefore, our truth table should read, with a logic buffer gate, when the input is off or 0, then the output is off or 0. Now we shall reset the simulation and close SW1. Reconnect the power, and as before, the route is through R1 to SW1 and through R2 to LED1. This time, however, power or signal switches TR1 on, and the circuit is complete, allowing LED1 to illuminate. Our truth table for a logic buffer gate is when the input is 1, the output is 1. As before, let's construct a circuit using the breadboard. But first, the components we need: 2 resistors, a switch, a transistor, and an LED. These symbols are then substituted for the components along with a couple of links. We bring back our breadboard and start the construction. It really does not matter which component we start with as long as we follow the schematic diagram. In our example, it is a switch. This can be found on row 22 and 21. When the switch is on, then row 22 is connected to row 21, as shown. R1 is connected to the positive terminal on one side of the switch row 22. Again, the transistor could be positioned anywhere, but we have chosen row 20, 19 and 18. The negative of the LED is connected to the collector of the transistor, row 18 to row 17. A link is used between row 21 and 19, which is from the live part of the switch to the base of the transistor. A further link is made between the negative and row 20, which is the emitter of the transistor. And finally R2, which is connected between the positive and the positive connection of the LED. We now bring back our truth table and enlarge the working area of the breadboard. In our schematic diagram, we have an electric route marked out, and it travels to R1 and to the open switch as shown. Now we turn our attention to the breadboard. As before, the route is along the top row through R1 and to the switch. Back to our schematic diagram. The route continues through R2 towards the collector of the transistor, but because the base of the transistor remains at 0, no current can flow through the transistor. In our breadboard, the same thing happens. The route is through R2 to the LED, but because there is no voltage at the base of the transistor, there is no path through to the negative and the LED remains in the off state. Our truth table for logic buffer gate is when the input is 0, then the output remains at 0. Now with the schematic diagram we close SW1 or our input, as well as the switch on the breadboard. The route is then traced around the schematic diagram to the closed switch, and then around our breadboard. Now the switch in our schematic diagram is now closed, current can flow to the base of the transistor, switching it on, and current flow can continue to the negative of the battery, switching on the LED. So in our logic buffer gate truth table we should read when the input is 1, then the output is 1. We should be aware that although we see in our schematic diagram the switch SW1, it represents the result of a previous logic gate, and the output, which we have used, an LED, is the result of our logic gate that could be part of our next logic gate. This simple logic gate is the building block on how our computerized systems work. It could, for instance, be one single bit of an 8, 16, 32 or even a 64-bit computer. Next is the logic AND gate, which has two inputs and one single output.